Hello. My slides are visible?
Yes, sir.
Yeah. Shall we start or should we wait?
Yes, sir. You can start.
Yeah. Good afternoon, everyone. Let me start with another topic, and which is unsupervised learning. Before I go to that topic, let's summarize what we have studied yesterday. So yesterday we discussed about one of the important problem in machine learning and AI, which is the classification problem. Classification is about taking a data and classifying into either one or two or more than two numbers, like 0, 1, 0, 1, 2, etc., where each of those numbers indicate a certain class. The class is defined as a data which has certain features. For example, we discussed benign versus cancerous tumor. Then benign is a one class, benign tumor is a one class, cancerous tumor is another class. Fraudulent versus genuine transactions is basically two classes. So we have studied those kind of problem where we learned how to find a class boundary, because given the data, we want to predict whether this particular data belongs to class 1 or class 2. Or in example point of view, given a tumor images, we want to say that whether it is a benign tumor or it is a cancer tumor. Or given a transactions detail about its location, amount transaction, where did it happen, how much, what did person buy, all this detail. Using that detail, we want to know whether this is a genuine transaction or it is a fraudulent transaction. So that kind of transaction, when we want to learn, we have to find a boundary which separate these two classes. And we learned several linear and nonlinear classifiers to actually find out this class boundaries. We learned particularly logistic regression, which is one of the simplest model, which use regression ideas to the classification. Second one we learn is a naive-Bayes classifier, which is a very simple classifier based on the Bayesian approaches we have learned during our high school. And we can see that we can actually extend those high school concepts to a very complex task-like classifications. And also we learn K nearest neighborhood, which is another approach to make a classification problem, to solve classification problem. In addition to that, there are other more classifiers which are there in the literature, like perceptron, support vector machine, neural network are more advanced and more complex algorithms to actually learn class boundaries. With this, I'll start today's class, which actually is about unsupervised learning. So far, in a previous 2 or 3 classes, we have actually learned concept of supervised learning. What does it mean by supervised learning? That we have a data, in that each data has some label associated with it. If I have a set of features, I know what is some number which predicts either class or some quantity in a regression problems. So it is like a supervised. I'm giving data to my model, which has a both. What is the what you call it, input, and what is the output? What is required and what is the want to predict using this model. Now there is another set of methods which is called unsupervised learning techniques. The objective of unsupervised learning techniques is to actually build a model or discover different patterns given only X. There is no label associated with it. For example, if I give a mix of, let's say, rice and some kind of lentil, that's a mixture. And I don't tell you basically what is rice or some kind of lentil. What will you do? You actually have to separate it out, correct? And create a two cluster. Here, a priori, you do not know what is a rice, what is a lentil, but you know that rice has these objects have two kind of shapes. One is something like ellipsoid, another one is a round and thin. So some features which your eyes use to actually distinguish this two objects, and you know that you can actually separate two objects. But you have not labeled them as a rice or lentil. So whole job of unsupervised learning is to learn using this data where there is no label associated with any of the observation. You don't know with this. If I give you rice picture, you don't know rice picture. I give you lentil picture, you don't know lentil picture or dal picture or what call it. We don't know that, correct? But when as a human being, we know that these are two different objects, even if you don't know their name, correct? So, but if I give you the mixture of them, you can separate it out and create two separate, what you call it, heaps or cluster, which actually can be defined as a one object and another as another object. Right? So unsupervised learning performs something similar. They actually try to create a two heap or create two or more clusters. You do not know whether those clusters have some formal label, but you know that this particular cluster has objects which are quite similar. Another cluster has an object which are quite similar. And that's what unsupervised learning does. Unsupervised learning try to actually capture relationships or nearness of the different observations. So what is simple example I can give here is a set of images on the left hand side, okay, which are images of tigers and elephant, the way we know as a human being. But if you show these images one by one to the kid, like toddler of 2 years or 3 years, and try to ask the kid that, can you actually give me similar images? What will happen is that kid will actually look at it and realize that this can be a kind of tiger, this can be an elephant, correct? And here they do not know what is an elephant, what is a tiger, but they still can actually, by some association, some pattern they will learn among the data and realize that this can create one group and this can create another group. And that same idea is exploited by algorithms. In unsupervised learning, what the algorithm will do is, will take this set of images and create two clusters. The cluster number 1 is here, cluster number 2 is here. This is for the supervised learning algorithm or this algorithm. It is the images which are near to each other in a certain sense. For a trained human eyes, you can see that, okay, if I give you, I don't tell you it is a tiger, or I give you some animal, which you have no clue, have you never seen. But I give you a set of images of those animal and elephant. I'm sure that you can distinguish elephant from those other without knowing what is the name of that particular animal. The reason behind here is, even if you don't know, you know that there is a similarity between the image in this and this and this. And that's what unsupervised algorithm does. They take these images and find out similarity between them and create two clusters. What they are saying is, this is the one kind of images which are similar. This is the second kind of images which are similar. And as a human being or as an expert, when I go and look at it and I say, yeah, this is elephant images and this is tiger images. So what is the unsupervised learning? It will take these images without knowing what are the label associated with it. I'm not labeling at all whether it's a tiger or elephant. I'm giving to my algorithm and it actually creates two clusters or 3 clusters depending on these images. Is that clear? If that's clear, then we can talk about what is more formally unsupervised learning. So unlabeled data, okay, are huge in the world. Okay. For example, I'm giving a first task here is automatically categorizing news items, IIT Madras research related news. Okay. So it's unlabeled data. If you actually go it, every time I have to go and search IITM and do it. Right? I want computer to find it out that this is the news item related to the IIT Madras. Okay. Find an anomaly on lung image related to TB. That's a unsupervised, unlabeled. I have given you image. That's it. I'm not going to tell you it's a TB or not. I want to find out there's an anomaly in the lung. It can be lung cancer also. Find a customer preferences or persona from the shopping pattern. This is the one of the widely used application of unsupervised learning. They don't know what you are buying, what I like. There is no neither associated with my customer. I might be buying from some other for someone else. So here they want to actually look at customer preferences or persona by shopping pattern, and they may not have any idea about who is the customer. And there are very interesting patterns people have actually found out, and very funny examples people have actually found out that if you, for example, one of the data which people have analyzed is just a transaction by customer. That's it. And using that transaction, they want to find it, give a promotion. And they found out that it would be nice to give a promotion for a beer and the baby products together. Because whenever this is the computer is saying, algorithm is saying, and it's very, very strange, correct? Something which is for the adult and something which is for a kid. Then people did a social experiment. People realized that because often what happens is in a Western world, at least, when people have a baby, people do not have time to go and hang out and have a beer. So they actually buy and hang out at home because they cannot go. So that's very unusual pattern people found out from the unsupervised learning. So, and then after that, they actually correlated that phenomena with what is the reason behind that. And of course, it has its own societal implication about policies. What I'm saying is that unsupervised learning data is always unlabeled data. And often people found out very interesting pattern. And they have used that without knowing who is underlying the person, whether it is a mother buying, father buying, sister occasion. No, it is a transaction which is anonymous transaction, and it gives the pattern about our social behavior under certain conditions. So there are different kind of methods actually people use to actually analyze the unlabeled data. First one is the clustering analysis. The example of taking a tiger and elephant, or rice and lentil or pulp, okay, distinguishing. That's a basically cluster. I have created 2 clusters here. I don't know what is tiger, what is elephant. Only thing is I know that these objects are similar. These objects are similar. Right? That's called clustering analysis. I'm clustering them into set of similar objects. Second one is dimensionality reduction. That's a little bit of technical word, but let me explain you in different manner. Okay, in many industries, they have a sensors. The sensors, for example, a simple example I can give is flow meter in a pipeline. Okay, so where basically in any water distribution pipeline, there will be flow meter. Okay, and now the question is how many flow meter I need to measure this data. Do I need 1, 2, 3? For each pipe, I need 1. So people cannot find out that easily. So what people are saying that there might be some relationship because water comes from the main tank. There might be overhead tank nearby your area, and the water will flow and give it to different houses. If I put my sensor, a flow meter every places, then I can tell that how much I'm giving to the X person and how much I'm giving to the Y person. So how many those sensors I need to actually find it out is a dimensionality reduction problem, where I need only some flow through some pipe or flow rate of some pipes, and remaining pipe I can construct. So that's called redundancy in the data. That our feature, which are actually giving rise to data, are actually less compared to the number of variable I have actually counted. Okay, so that is where the dimensionality reduction come into play. So I need two sensor, but I have employed 3 sensors. Okay, so instead of that, I need only 2 sensors. I don't need 3 sensors, but I employed 3 sensors. So my real data actually has only 2 dimensions. So first, we'll start with the clustering analysis. The clustering analysis, as I told you, is a cluster is a collection of data objects similar to one another with a same cluster. So as the same as a elephant and tiger. If tiger is there, I will try to see another image, whether it is an elephant is there. I want to know whether the new image belongs to tiger cluster or elephant cluster. And of course, by visual instruction, I will say this is belongs to tiger. So I will put in tiger. Another image comes, I will see elephant or tiger. If it's near to tiger, I will put it tiger. If it's near to elephant, it's elephant. If it's not near to either of them, I will create a third cluster. Then again, I will keep doing for similar. And these similar objects, as I told you, to the object is in other clusters. Okay, so that is basically clusters, which has a collection of the objects. And cluster analysis is basically a task of finding a similarity between different objects using which are basically comes in the forms of data according to characteristic found in the data and grouping similar data objects into a cluster. So let me go back again and explain this example. These are the 8 data points I have. Okay, and these data points, I don't know a priori what is tiger, what is elephant. What I know, I have this 8 data point, and what I will do is I will try to see the similarity between all pair of data points. And then I will actually rank them in the similarity. And as a human being, when I give, or even I give it to a small child, what it will do is, she'll figure it out that these 4 should be similar and these 4 are more similar. Correct? Am I right? Based on their interior. They may not know what is tiger, what is elephant, but they can know they are just similar. So that similarity is what characteristic we found, we actually exploit. So for example, someone will use the characteristic of this big teeth, or trunk, or the color, gray color, more or less, or they will use the tiger facial expression, color, black stripes, etc., etc. So you can actually exploit certain features and try to see how similar they are to each image. If I compare this image with this image, black color is, the stripes are not there. There is not a huge teeth or tooth of the elephant, and they say there is no tooth at all. There is there is no trunk here. There is no trunk. There is a trunk here. There is no trunk. So what I'm saying is that there are different characteristics which we can say that, and we can say that these two are not same. So, but if I do compare with this one, I have two are same. There is a white, black stripes, orange color, same kind of facial features, etc. So those characteristics has to be used within the data. I'm not telling you whether what is a tiger and what is a elephant. I'm just giving you data, set of data. In unsupervised learning, that's why there's no predefined classes or predefined labels. We just make a cluster out of it and then examine those clusters and find out what are those common characteristics, and may decide to provide certain labels. May. It is not necessary that we have to provide label. We may decide because it makes life easy sometimes. As I told you, typical application as a standalone tool to get insight into data distribution as a pre-processing step for other algorithm. It can be used for pre-processing step because it may help us to do efficient pre-processing, or sometimes it is just used to understand what kind of similar object has a distribution. And clustering has a very rich applications and multidisciplinary efforts. It used to find out patterns in a different data sets. It can be weather pattern. It can be pattern in terms of what you call it, machine signals, etc., or usage of your mobile. Spatial data analysis, creating thematic maps in GIS by clustering feature space. Okay, detecting spatial cluster for other spatial mining tasks. For example, we have a set of data. One of the great work done by IIT Madras is trying to understand the quality of air in a different part of city. What you do is you actually take a quality of air, and some of this quality of air is done through auto rickshaw, which you do not know which road it travels, but it collects the data. And what people do is people actually use GPS of the mobile, and sometimes if auto has it, to actually find it out the good cluster in terms of good quality of air, poor cluster where the poor quality of air. It is used for image processing. Many of the things we do it on our mobile, many apps we use cluster analysis to actually figure it out where your ear is, or where is your nose is, and accordingly some funny feature they will add so that you will see that a person has gone bald or gone aged. Okay. In the market research, it is widely used. Document classification. If I want to classify different documents belongs to history of Tamil Nadu, or document belongs to what you call it, industries in India, or etc. For any kind of documents in the WWD, and I want to classify them, then clustering can be useful. They will find a pattern because you do not know how you should actually, first of all, classify. You need some data to actually create the classifier, because classifier requires label data. There is no label data. So you have to actually use clustering approaches to get the patterns and the document clusters, and then examine them and say that this belongs to Tamil Nadu history, this belongs to Telangana history, etc. Cluster weblog data to discover groups of similar pattern. This is again another example. In marketing, it helps marketers discover distinct groups in their customer bases. Okay. And land use, identification of areas of similar land use in the Earth observation databases. Insurance, identifying the group of insurance policyholder with a high average claim cost. Here you don't have to know individual. You just basically use the data and find out the cluster. In a city planning, identify the groups of the houses according to their house type, value, and geographical location. Earthquake study people are using to find it out, faults, continuous faults, and finding out earthquake epicenters along the continuous fault lines. These are very, very diverse application of clustering analysis. One of the major challenge is finding out a good cluster. How do you know there's a good cluster? For example, of tiger and elephant, when you look at the cluster which has a no elephant is put in the tiger cluster and no tiger is put in elephant cluster, it's a good cluster. It's not even a pure cluster. It's called purity of the cluster. It has a similar kind of data set, as many as possible. Because sometimes, because of, for example, if someone has actually put a colored this elephant with the orange and this one, orange color and with the black stripes, we might classify that one as an elephant. So that's called noise. So if someone has actually done that, then there will be a 4 elephant and 4 tiger and 1 elephant picture, which looks like tiger. So good cluster method will produce high quality cluster with a high inter-class similarity, okay, or low inter-class similarity. So let's go back. The good cluster here is when you look at the similarity between these figures are very high, but similarity between these two is very low. That is the good cluster and clustering approach, which approach allows you to create this kind of cluster or good clustering algorithm. The quality of cluster results depend on both similarity measure used by the method and its implementation. Now, this is a detail. Now, the question we are going to ask is, if I give you 2 images, how you actually, as a machine, will actually figure it out 2 images are similar or not. So I have to actually define certain approach. See, for our brain, it is very easy because we have been trained over a time and reinforced that this is a tiger, this is a tiger. Or our brain over time, by observing and imbibing so many visual can distinguish different kind of shapes, objects, and everything. So we have a certain similarity measure. Sometimes we get also confused by looking at some same persons. We can confuse if we met only once or twice, correct, with some other person, because our similarity measure will not allow us to distinguish between that person and this person, or we will not recollect that person's image because that data is not there. The similarity measure basically try to understand that whether how similar particular image or particular data is from the another data which you have given to it. And of course, how we actually implement this also matters, because sometimes if we do not implement properly, we get a poor cluster. Sometimes quality of the clustering method is also measured by its ability to discover some or all the hidden pattern in the data. How we can measure the quality of cluster? So similarity is expressed in terms of distance function, typically metric Dij, and there is a separate quality function that measures the goodness of the cluster. Okay. So first thing we have to do is we have to generate a metric, which basically here is some kind of score we are giving for similarity between the object I and J. And there is again, once we do that, we actually have another function of this Dij, which tells us how good each cluster is. And that's why the definition of distance functions are usually will come into play. And the distance functions are Usually very different for interval, scale, Boolean, categorical, ordinal, ratio, and vector variables. So depending on what kind of variable you are actually handling, there might be different distance functions, which actually talks about quality. So I cannot take something which is continuous, like say height, and so I have to, let's assume that there is two features. One is the height, another is gender. Okay. Then height is defined in terms of centimeters. Gender typically defined in terms of male and female. Okay. And we actually can convert this male and female as encode as a 0 and 1. Okay. So now there are two kinds of data. One is a categorical data, other one is interval scale data or continuous data. I cannot use same definition of distance to actually handle them. So we have to be careful when we actually define the distance function. But many methods will have their distance functions, and this is also active area of research where people are coming up with a more and more distance function. Furthermore, sometimes depending on the data type, people associate weight to different variables based on the application and data semantics. And remember that it's very hard to define similar enough or good enough. And it's very subjective when we actually do it. For example, same goods, which I feel good, you may not feel is good. So we have to be very careful when it comes to similar defining distance functions and similarity or dissimilarity metrics. And the clustering requirements in a data mining is scalability, ability to deal with different types of attributes. So attributes is like, as I told you, height, gender, etc. Sometimes we have a data which change with the time. Those are called dynamic data in some sense. So how to handle them is also a question. Discovery of cluster with the arbitrary shapes. Means arbitrary shape means very cluster which has a not a very simple shape. It can have a very unique shape. So how we can discover, because that's one of the challenging part. Typically, many distance functions are trying to create very smooth shape, but there are things where we can have an arbitration. Most important part, minimal requirements of domain knowledge to determine the input parameters. So in a cluster, clustering techniques use such that it does not depend on the domain of application. Domain of application can be, your clustering can be used for the image clustering or clustering of winners in different years, or the clustering of numerical values. The clustering algorithms should not depend on those kind of where the data is actually generated. Whether it comes from the agriculture, it comes from the computer science, or it comes from the industrial or mechanical engineering department. No, it should not be. Another thing, its ability to deal with the noise and outliers, particularly noise. Each of these images, sometimes you get a good image with the higher resolution camera, you get a poor image with the high resolution camera. But with same different kind of images, poor or good images, your clustering algorithm should be able to distinguish if they are different images or same images. Insensitive to order of the input record. Doesn't matter which order it comes, it should be able to give you a same kind of cluster. High dimensionality, it can actually handle any number of variables, 1,000, 2,000, 3,000 number of variables. Incorporation of user specified constraint. It can actually handle if there are constraints available to you. For example, I want to actually find out cluster where I can say there are only 3 clusters should be there. That's my intuition. So that user defined constraint on number of clusters. So it should give only 3. Then we should discuss interpretability and usability of the algorithm which we got. In other words, can I actually interpret the results, or I actually can go back and see whether I have discovered clusters which can be useful for my intended application. If I cannot do it, it's useless. So for example, we have a huge project with one of our colleagues who works on a maternity, what do you call it, preterm birth. So in India, many kids born before their gestation period, and because of the premature baby, have a lot of complication. So these people are trying to build a model for that. And a couple of days ago, they came and said that we want to know what are the important metrics which we should measure to actually distinguish between the preterm birth mothers and normal mothers. Because the cost of measuring different features is very high. So we want to know, can I actually distinguish you? They want to use clustering algorithm to find out what features allows them to distinguish these two mothers. So here the usability and interpreting comes into play. I want to interpret such that I can actually go back, and the next time when I perform my experiment, okay, at that time I will not measure all variables because it's very costly and sometimes it's painful to the mother. So I will measure only very subset of them. It's cheaper and faster. So the clustering algorithm should be in that manner: interpretability and usability. Major clustering approaches can be distinguished into 3 types: partitioning approaches, hierarchical approaches, and density-based approaches. So what is a partition approaches? It constructs the various partitions and then evaluate them by some criteria. Minimize sum square of error is the one criterion. Typically like method like k-means, k-meteoroid, glance, those kind of. So let me again explain how partition system works. This is one of the example I can take. I still have some 15 minutes, so I'll take a simple example. So I have this set of data, and you can see how many clusters are there. Technically 2 clusters, and I don't know whether what is this arbitrary chosen object which belongs to which cluster. I don't know. So what I will do is I'll first start with assign each object to most similar cluster. So I did that, and I did this also. Okay. Then I update the cluster mean. So I computed the cluster mean. So what is this circles? Cluster mean is basically there's a definition to this. This is some kind of distance metric. Using this cluster mean, I have reassigned the different point, and then again update the cluster mean and reassign again, and keep doing until I get no changes in after computing the cluster means. Okay. So in the partition one is you start with a 2 partition, 3 partition, and keep updating the partition. In hierarchical approaches, you create a hierarchical decomposition of the set of data or objects using some criteria. So for example, it is like you have a data and you use 1 point criteria to actually decompose. Then you go another one decompose and create a hierarchy of decomposition, which finally tells you that which cluster it should belong to. And there are another interesting method called Dyna, Engage, Burke, Rock, Chameleon. And they like this kind of words. So that's why they kept it. The last one is a more technical term. And it talks about, it looks at the distribution or density function of different clusters. And also sometimes use some connectivity metric to figure it out whether those clusters are near to each other or not. DB scan, optics, DentClue are typically density-based approaches. Then there are other clustering approaches, grid-based approach, where we will look at the based on multiple level granularity structure. Typical method are stinged wave cluster. There are model-based techniques. There are frequent pattern-based technique, and sometimes constraint-based techniques are also there. So I'm not going to go to this. I'll provide you the slides about this, but we'll look at some method called K-means clustering, which I was also trying to explain you earlier very quickly to understand that how clusters are changing with each iteration, and we'll see that method. So here I have given some idea about a center or centroid of a cluster for numerical data set. The center is the middle of the cluster. CM is the summation of 1 and Ti by n. The radius is basically square root of average distance from any point of the cluster to its centroid, this one particular point. So what is the distance? What is the diameter is square root of average mean square distance between all pairs of points in the cluster. There are two different approaches. In the partitioning method, what we do is we construct a partition of the data set D of n objects into a set of k clusters using mean sum square distance like this. Okay, so you have a k cluster is defined. So we have given k cluster. I need a 3 cluster, 4 cluster. We give, and then now the objective is find out which. It's like a bean bag. Okay, I gave you 3 bags, which means 3 cluster, and now you have to figure it out what object goes to what bag. That's a partitioning based method. So I have given you how many partitions I need how many clusters I need, and then I optimize my given cluster by choosing some partitioning objective or criterion, which is this one. Global optimal. If I want a globally all perfect solution where I can actually distinguish each object using this criterion, then I have to do is I have to look at all possible partitions and find out what object should go which part. Another one is heuristic method, where we look at only k near points or k means or k methods and figure it out about clustering approaches. So let me talk about k-means clustering. So in the k-mean clustering, one second. What you do is following. It's a very simple algorithm. We have we decide with a k. K is basically gives you k subset of the object and partition object into k non-empty subsets. If I give you k is equal to 3, you will look at 3 bags in which you have to put each point. Now start with a 1 point or set of points and compute the center of this point. So you for each empty set, non-empty set, you actually compute the center. And using that center, you actually measure the distance of all each object near that center or in the cluster or nearby cluster. And then based on the distance, you decide whether this point should be reassigned to the new cluster or should we keep in another cluster. And you keep doing it, and then again you go back to step 2, you again do the compute, because now you have a different every time you are reassigning based on the distance. Every time you're think this way, every time in your bag, the number of objects will change, and hence the centroid will change. And hence you can actually again go back and recompute. You can keep doing it until you have no more new assignment. You cannot actually change the centroid at all and assign a point to the other cluster or bag. So that's what I was explaining here. So you have this object. Hello, yes. Yeah. So think this way, that I have given you this object, okay, and I don't know where this red point actually belongs to. So what I'll do is, I have taken arbitrarily some object and assigned to created 2 clusters. Using these 2 clusters, I will find the center of this cluster using this 1, 2, 3, 4, 5, 6, 1, 2, 4. I'll do that. Now, what I will do is, I'll do interesting part. I'll go back and I will update the cluster mean based on what I have computed here. And now what I'll do is, I will actually somehow go back and see with this new updated cluster mean, what are the different objects near to this mean. If I do that, I'll realize that this particular point, visually you can see it is near to this cluster, which is this blue cluster, and the another cluster, what you call it, near green cluster. These 2 cluster, this point is near to this cluster, and this point is near to cluster, and then you can keep updating based on new reassign the point, because now this is near to it, so I'll reassign it as not a blue, as a green, and this one near to this cluster means, so I'll assign it as a blue rather than not a green. And after updating, again I will find a cluster mean and keep repeating it. And when new point comes, I will look at it, new k neighbors of this one, and figure it out where this cluster belongs, this point belongs to. Okay, near to this center or near to this center. Okay. So that's basically k-mean clustering method. So what is the strength of k-mean? Okay, so the interesting part of k-mean is it actually is a relatively efficient method. It means if you have 2 million objects or points, it will still give you faster results. The only problem is you may not get the best result. You will get a good result, but not the best result. That's a local optimum, and the global optimum may be found. If you want to find the best result, you have to actually use very advanced optimization algorithms. What are the weaknesses? Applicable only when the mean is defined. That's a very important part. It means that about categorical variable like male, female, first rank, second rank, third rank, those kind of places I cannot easily apply this kind of techniques. Need to specify k. I have to tell how many clusters I'm looking for. That in advance, that it cannot discover how many clusters are there. That's one problem. Unable to handle noisy data and the outliers. If there is an outlier, it will be very difficult to actually figure it out using this technique. And non-suitable to discover cluster with the non-convex shapes. Or these are technical terms, you don't need to worry about it. But what it says that certain kind of shapes, the k-means cluster cannot actually discover. Using the techniques or algorithm, we cannot discover certain steps. But it is very minor shapes, don't worry about that. But one of the major problem here is specifying k and noisy data. So I'll not come to that part. The hierarchical clustering, I'll explain you very simple manner before we still have some time. So I want you to ask some trick question. What we'll do in the hierarchical clustering, we try to create some kind of clustering criteria or distance matrix. Here we do not require number of cluster, but it requires some distance between different objects and some terminal criteria when I am actually saying that, okay, I'm happy with the what you call it, this number of clusters. Okay. And there are different approaches to actually hierarchical clustering. One is a top-down approach. Another is bottom-up approach. One is agglomerative approach, where you start with the individual. So you start with the 5 clusters and then ask the question that which 2 clusters are actually should be merged. And then here you can see the AB has merged, and here they have merged first DE, and then these merged with the D is merged with the CD, and after that AB and CD merged to ABCD. Okay, and you got a 1 cluster here at the end. Now each point you will have a certain criteria which basically tells you that by merging you are not improving. So there is no point of merging, and it will tell you number of clusters. Second one is the divisive approach, which is a Dyna algorithm, which start with a global cluster, 1 cluster, and then try to figure it out whether you can divide this cluster into multiple clusters or not, based on certain criteria. And there are some way of actually figuring out different distance metric between these clusters. In general, we have different alternatives to calculate the distance between clusters: single link, complete link, average, centroid, medioid. Okay, and you don't need to worry about it. It's just a give you idea that there are different way I can actually measure the distance between 2 points when I want to actually look at the similarity or dissimilarity or distance between 2 points to decide whether it belongs to same cluster or different cluster. This has been already discussed. So I don't have time to discuss about ANGAS. It's again another algorithm, as I told you. It starts with the ANGAS is, remember that it is start with the individual and then goes towards the agglomerative point of view. So it starts with the 1, 2. Here I have only looked at 1, 2 and remaining point. Then based on some metrics and the link I had it here, I have actually created 1, 2, 3, 4 points. Then I actually merged them again and got 2 clusters. And I can actually merge and get a bigger cluster. But remember that when I did that, I realized that the dissimilarity is very high after, so there is no point of merging it. So after that, you stop merging and you actually stop at the metric where there is a dissimilarity. So there is some kind of criteria, terminal criteria, which says the dissimilarity about this, you should not merge, dissimilar below this, you should merge. Okay. So that's here I actually end up with a 2 cluster. There is another way of looking at this. One is we are using a dendrogram. Dendrogram actually does this following. It actually starts with a decomposed data object into several levels of the nested partition tree or clusters called dendrogram. This is basically dendrogram. And the clustering of the data point is obtained by cutting the dendrogram at the desired level, and then each connected component form the cluster. So for example, I started with this one, and then I try to get, these are 2 clusters right now, and then it becomes 3. And then after that, there is no point of actually increasing this cluster, 3 points, and these points are very different. Similarly, I do start with the individual one and come to this one. Okay, here only 2 levels. Now, what happened is that is following. if I actually divide at this level, if I put this as my criteria, then each of these points is an individual cluster. But if I do this way, then there is only one cluster, two cluster, three. The green, all the green are the clusters. If I use this as a criteria, then all one cluster, two cluster, three cluster, and four cluster. But if I use the blue as a criteria, then I have a 1, 2, and 3 cluster. So depending on the criteria, Dendrogram will tell you how many clusters are there. And there are the interesting algorithms to solve the problem. So the last 5 minutes, what I want you to do is, instead of I go and talk about Rocky and other things, similarity measures in Rocky, I don't want to talk about those things. What I want you to actually, there's some density-based clustering approaches. Let's not worry about it. What I wanted to ask you is, if I give you a set of example, you can apply any of these algorithms. Now, what is the question important? Which algorithm to use when? So, for example, I'll start with the last one. It is called DB scan. The DB scan is typically used as a pre-processing step in many algorithms to find out outliers. So it is not used as a clustering approach, but it is used typically to find out outlier in the data. Okay. Similarly, and DB scan is very sensitive to parameters, and that's why it provides very interesting results often. For example, if you look at it, depending on any shape, DB scan is clusters very well. Similarly, there is a method based on called chameleon, which is clustering complex objects. So it can cluster different kind of objects, a different shape of objects, almost like a human being does it. And that's why it is used often in some of these pattern recognition techniques, or figuring out a cluster which has a different kind of objects. And of course, it used some kind of graph-based approaches to do the analysis. So this is where many of these algorithm works. What I want you to know, if you have any questions, can you please ask today's class, tomorrow's class? Any questions regarding clustering algorithm, unsupervised learning? Then next class, I can talk about some dimensionality reduction and some simple application of deep learning approaches in a day-to-day life. No questions? So again, I think Indu will teach you all these techniques, how to implement them. Of course, algorithm, you do not need to understand on algorithm right now in detail, but you can understand the idea, and you can apply some of these techniques. I think she'll teach you Dendrogram, just to tell you. So you should look at some of those methods again. K means she will teach you hierarchical clustering, because it is widely used in the literature. We use it very often to actually cluster different kind of data and try to understand those data. Dendrogram is very easy way to actually cluster. So you will see many histograms. Hierarchical clustering actually explained in terms of dendrograms. And So of course, we use ROC algorithm often to actually do cluster the category variables. Particularly, as I told you, one of the examples related with the preterm birth, which is a big project here. The chameleon is not that widely used by us, but there are other people who use it for clustering the image data and when there are clusters which are very nearby. And density-based clustering approaches are typically used by at least me, as for example, DBSCAN and DenFlu. We use for finding out outlier in the data. So please, if you have any questions, please ask them. Again, please go through the notes and let me know. We'll meet on Monday or Tuesday. I have some administrative meeting, madam, on Monday. I don't know what time it is because my presentation. So may I request
Okay,
that
sir.
if it's possible to do on Tuesday or Wednesday?
No problem, sir. We can.
Yeah, because it's started 3 o'clock, but I don't know when my presentation will be.
No
because-
issues. Then we'll have it on Tuesday, sir.
So yeah. So I'll Tuesday would be difficult because it is possible, but I have a class from 3 to
Okay.
4:45.
Okay.
So I'll see.
You can message me later, sir, so that we can do it.
Please, ma'am. Thank you very much for your
Thank you.
understanding.
Thanks a lot, sir. Right.
Thank you. Thanks.